So, if this works, which I've never done before, then I guess the podcasts will be available on the podcast website where they are. Plus video, which I think is pretty cool, because I always wanted to see a video of myself teaching, but I never have. All right, anyone still having problems? Yeah? That's another option. There's two types of video. There's people that can just capture whatever they post on the projector, or and I think I'm getting filmed right now. There's an auto-tracking camera back there that automatically picks up my movement, and should, if it works, I haven't seen this yet in action, but it should be available within like 12 or 24 hours after the lecture, I think. So I'll see if it worked and if it picked me up. Let's see. Anyone still having problems getting on WebAssign? So the people that approached me at the end of class on Monday, you guys figured it out, I guess? Okay. Cool. Yeah. Okay. Okay. So, we ended class on Monday with a nice little proof of the fundamental theorem of calculus part 2. So I'm going to finish that off today. And what I proved was that if I define this function a of x to be the integral of f of t, what I showed on Monday was that a prime of x is equal to f of x. So this is basically the fundamental theorem part 2, but let me just slightly rephrase this. Basically, I'm just going to change the notation a little bit to write it the standard way that it's usually written. So here is the official statement of the fundamental theorem of calculus part 2. Okay, so it's the same as this, but we usually use the letter F, capital F. I'm just going to rewrite this, except you usually use a capital F, which is, okay, so if capital F of x is equal to a to x little f of t dt, then capital F prime of x, it's just like you take the ending point and you stick it inside the function. So is little f of x. That's the that's fundamental theorem part 2. More compactly, I'm going to write it a third way, just a little bit more compactly, as d dx of the integral from a to x f of t dt is, once again, you just stick the x into the function. I would like to point out that you'll notice this pesky little a appearing, the lower limit in the fundamental theorem. And that A is kind of immaterial. It doesn't really matter what it is. No matter what it is, this still holds true. Choosing a different number for A just kind of shifts this by a constant, which disappears once you take the derivative. So that's why the A there doesn't really matter. So let me give you an example. And let me just write that note that I just said. You'll see where the A comes into play. So here's an example. Let's let f of t equals sine t squared. And let's see what the fundamental theorem of calculus part 2 says about it. All right, so I'm going to try to graph this guy. Here's t. Okay, that's roughly what the graph of y equals f of t looks like. Let's see, here's the point root pi. Here's the point root 2 pi. I'm going to choose an antiderivative satisfying satisfying that f of 0 is 0, i.e., f of x will be the integral from 0 to x of sine t squared dt. So I'm choosing f to be the area starting at 0, going up to whatever my point x is. So for example, if x is right here, then I would add up this area, but then subtract off the yellow area. Notice this part about f of 0 being 0. F of 0, according to this expression, is the integral from 0 to 0, which is a fact I pointed out on Monday, that if you do an integral that starts and ends at the same point, well, that's just always 0. So, all right, that part's good. Now, let's talk a little bit about this capital F that I defined. Someone tell me, what is f of root pi? Well, you don't have to say exactly what it is. Is it positive or negative? It is positive. In fact, that's the green area in my picture. How about f once we get to root 2 pi? So that's going to be the green area, but then plus this whole yellow area. Can you guys tell from my picture, should that be positive, negative, or 0? It should be positive because the green area is bigger than the yellow area. So it's true, like the yellow cancels some of it out, but it's still it's smaller than this one, but it is still positive. What it's equal to actually is it's equal to the green area minus the yellow area. Okay. How about the derivative, though? So if I picked a point in between 0 and root pi, let's say, here, okay, forget about this x. Let's say x is right here. What's the derivative at that point if x is between here, if x is between 0 and root pi? Can anyone tell me what the sign of f prime should be? Are we adding more area at this point, or are we subtracting off area? We are adding because the function is positive. So at this point, the derivative is positive. On the other hand, if we are now in this region, so now let's let's call it z. How about right here? If root pi is less than z is less than root 2 pi, in that case, now we are actually subtracting off area, right? The yellow is negative area. So at this point, which I called z, f prime would be negative. Anyhow, the whole point of all of that is we can actually calculate f prime. I can write down exactly what f prime is. And the weird thing about being able to do this is, look at what f was. It was the integral of this function right here. Now, you guys don't have that much experience calculating integrals, but even so, does anyone know how to actually calculate this integral? You might think it's cosine, but then the t squared messes things up, and the chain rule makes it so it doesn't work. So even if you've already taken like 10 years of calculus, you still would not be able to explicitly calculate this integral. It's not possible. This is one of those ones, there's no other way to write this. There is no closed form here, as hard as you may try. So this is kind of like the only way to express this function. It is like a genuine real function. We just can't get like a closed form expression for it without having to write this integral. Nevertheless, we can write down the derivative using the second fundamental theorem, which says that the derivative of capital F is, well, we just plug in the x in place of t. So it's sine x squared. And that's that. OK. So that's it for this example. I'll come back to it a little bit more later. But let's kind of take a step back and talk about the bigger picture here. Kind of philosophically, what's going on with this fundamental theorem of calculus? Like, it's got such an impressive name. And if you can like really understand the fundamental theorem, both parts 1 and 2, that's kind of a sign if you're really getting calculus or not. So what the key fact, and I may have mentioned this before, is differentiation and integration are inverse operations. One undoes the other. And the two statements of the fundamental theorem are two ways of saying that. So let me write down like a little picture to illustrate. So the big picture here is that integration differentiation are inverse operations, meaning they undo each other. You get back to where you started if you perform both of them. So specifically, let's say I start with some function f of x, and let's see, what do I want to do first? Let's integrate it first. So I integrate it, let's say from, I don't know, some point, who cares, up to x, and let's use t as the dummy variable of integration. And then I take the derivative of this. What do I get? Back to where we started. Back to f of x. And that's what the FTCII said. What if I did it in the reverse order? What if I derivated first and then integrated? Well, that's what the first part of the fundamental theorem said. So let's do that one too. If I first take the derivative to get f prime, and then I integrate it. So let's say, let's just do it from a to x again. So a to x, f prime of dummy variable t. And according to the first fundamental theorem, this gives me f of x minus f of a. So this is first fundamental theorem. So did I get back to where I started? So kind of, like there's something a little bit off, this constant here. It's just a constant though, like don't worry about it. The point is like up to this constant, which you can kind of ignore and is a little bit pesky, we basically got back to where we started. So yeah, let me just say up to a constant. Up to a constant, we got back to where we started. Okay. Let's see. Am I doing my other example now? Oh, yeah. Yeah, let's go back to that example that I did, but I'm going to make it a little bit harder. And this will be a typical of your homework problems. Okay, so here's what I'm going to do to it is basically I'm going to mess around with the x up here. So now define capital F of x. It'll be the integral from 0 to x cubed of sine t squared dt. OK, so as you can see, I just replaced the x with the x cubed. And we're going to have the same question, which is to find f prime. So to do so, we're going to have to remember one of the most important things you learned in 20A, the chain rule. So let me refresh your memory on the chain rule. The chain rule is for taking derivatives of functions which are inside other functions, right? Function composition, so it looks like, let's say we have some function, and inside of it is another function which depends on x. And we want to take the derivative with respect to x of this guy. The chain rule says you first take the derivative of the outside, and then you multiply that up by the derivative of the inside. So you can also write it as df du times du dx. OK, so yeah, make sure you guys remember this. This is going to be your friend many times over, especially on Friday when we get to u substitution. Anyway, why do I bring this up? It's because it's what we need to solve for f prime. What do you guys think is going to be my u of x for this problem? The x cubed. All right. So we're going to let u of x be x cubed. So u prime is equal to 3x squared. And then f prime of x, which is d dx of, well, it's d dx of 0 to x cubed sine t squared dt, or let me replace the x cubed with a u. So 0 to u. So now's the part where I get to do the chain rule. And I'm going to replace this d dx by d du of the same thing on the inside. And I just have to remember to now follow it up with a du dx. OK. And do you guys see why I did all that? Because this is now perfectly suited for applying the new fundamental theorem, right? Now it looks exactly like, just kind of like what we did up here. If you take the derivative, you just plug in whatever's here into the function, into t. So that's the same thing I'm going to do here. I'm going to plug u in for t and get sine of u squared. OK, so that was here. So that was fundamental theorem part 2. And are we done? well, no, we're not done. We better put everything back in terms of x now. So I can now use this expression for u, and I also need u prime, so I get, if I plug in x cubed here, I get an x to the 6th. And if I plug in for this, we already calculated that was 3x squared. Okay, so there's the answer. So that's a pretty typical fundamental theorem type problem. Yeah?
How does it become sine u squared times du over dx?
That is what the chain rule says, right? Because originally I was taking d dx of something. I changed it to a d du of it, but then that means you have to put a du dx term on the end. So that was the du dx. This term right here is the same as this one right here. It's because, like, if I just tried to do d dx of this, I wouldn't even know what that is. Like, we only had a theorem for when it's like that, when it's just an x there. If it's something more complicated, you have to do the substitution here and use the chain rule like I did. It's the only way to do it. Okay, that wraps up 5.5. 5.6 is, so which means we're about on schedule. Okay, well, 5.6 is what we were supposed to be doing today, but it's a short one. 5.6, I only gave you guys 3 homework problems on. And what is 5.6? It's kind of an applications section, which is, what is it? Net change, integrals of rate of change. So yeah, a lot of rate of change business in a calculus class. It's kind of what it's all about, really. So let me start off with a sort of kinematics story, and I'm going to tie this into physics. How many people here are from LA? Nice. Yeah, I figure it's usually like a good 25%. Of any of my UCSD classes are from LA. I'm from LA, by the way. Who knows where Eagle Rock is? Nice. All right. Anyone from Eagle Rock? No way.
Yeah.
Nice, man. Sorry?
I'm like right there. Literally right next to Eagle Rock.
Dude, I grew up with the Eagle Rock Plaza. It's like at the bottom of my street. How about any from Glendale? Highland Park? Glass Hill Park? Echo Park, Pasadena. Okay, anyway, I used to drive up to LA often from UCSD to visit my parents. If you guys know, it's about a 2-hour drive, usually. It's taken me, like, if you go at the wrong time, it can be a 3-hour drive. One time I drove down to Qualcomm to see a UCLA game, and it was 4 hours. It's terrible. It was like gridlock the whole way. But my record was one time I waited till midnight to, this is a true, I waited till midnight to drive up there, and I sped up the 5 the whole way, and I made that trip in 90 minutes. Yeah. So you can do the math. I was going like 90 the whole way, except there's one time where they mess you up. It's that damn checkpoint, right? Stupid checkpoint. During the day, they don't make you stop. At night, like the late hours, they make you come to a complete stop, and some dude like looks at you, and if you look white enough, he tells you to just drive on through. Yeah, but you have to come to this complete stop, which like messes up my average for the whole trip. So let's say, okay, so I'm going to draw a graph of my speed for this trip. All right, so this is my velocity, and this is going to be time. So when you get on the freeway, you start from a stop, and then I'm going to get up to my cruising speed of, let's say, 90 miles per hour. And then right after Camp Pendleton, you hit that checkpoint, which come to a complete stop, really annoying. And then as soon as like you can't see the Border Patrol in your rearview mirror again, you go back up to 90. And then you make it to LA. Okay, so there's... Okay, so there's a graph of my speed, my velocity, excuse me. So let me talk about velocity for a second. Do this in the right order. What you guys, you've probably already learned that if, let's say, if S of t is my position at time t, then my velocity, which I'll use the letter v for, is the derivative of your position. I presume you guys have been exposed to this? Okay, so, wait, hold on, let me make sure I do these things in the right order. Okay. So, I just want to point out, like, note, for example, if I have a negative velocity at some point, what does that mean?
You're going backwards.
Yeah, I'm going in reverse, right? Yeah. Okay. And I want to point out, we're not going to use it for this example, but just like velocity is the derivative of position, what's the derivative of velocity? Acceleration. So acceleration a of t is v prime of t. The relationship between position, acceleration, and velocity is the basis of so-called kinematics. It's like the study of motion of things that move over time. And when you take physics, it's pretty much the first thing you're going to learn in a physics class. In a physics class that has calculus, this is pretty much the starting point of it. So all like very, very important stuff. I'm not going to use acceleration in this problem, but I want to point out, so in this example, going from 0 to, let's say, t, if I integrate this graph, which is a graph of my velocity, I better use another letter. How about v of r dr? No, how about tau? How about v of tau d tau? Oh, you haven't seen that one? I didn't want to use x or t. or s, because I'm already using s, so let's use tau. What is this? This is how far I've gone after time t. So it equals, well, in the notation that I just wrote here, it equals s of t. Technically, I should say minus s of 0. But, I mean, I'm assuming that, like, let's just say initially my position was 0, right? Like, if I want the position, the distance I've gone since time 0. So I'm just going to consider s of 0 to be 0 here. So in general, the integral of velocity, here I'll use a t here, from let's say time 1 to time 2 is your position at time 2 minus your position at time 1. And we have another name for this. It's a difference of two positions, also called a displacement. Okay. So and you guys know about how many miles it is to LA? I think it's about 110, yeah?
I have a question.
Yeah.
So the note that you're standing right next to, it says distance traveled after time t. Should it be distance traveled until time t?
Yeah, yeah, at time t, up to time t. Yeah. In time, how about in time t? So if LA is, let's say, 110 miles from SD, well, really, I should say La Jolla. How about from UCSD? So what that means is that altogether, this yellow area is 110 miles, okay? That's what the integral of the velocity is. It gives you your displacement. All right, so now I'm going to do an example. I'm going to do another physics one. Yes?
So for distance traveled in time t, I thought when we're working with distances like overall, I thought these were the absolute value. Are we not supposed to do that in this example?
Yeah, you're right. I was going to say, yeah, this is kind of a lie, and I should have been more specific, and I should have just said that. It's displacement, yeah. So this is, I should be more careful with my language here. So I actually had it in my notes. Okay, I lied. That's the actual truth. So technically, yes, it's your displacement. So in fact, let me just cross this out, and how about write displacement? And usually, like, it's usually convenient to say wherever you're starting at time 0 is position 0. So in fact, let me do that in an example. How about dropping should we say a cat from a tree or a kitten from a skyscraper? Okay, so, yeah. All right, so here's an example. acceleration of gravity on the Earth's surface is about 9.8 meters per second squared. Thus, an object dropped, if you just let it go, so, okay, it's like imagine you hold this kitten out the window and you just let it go. All right, so an object dropped from rest achieves a downward velocity because we're assuming that the acceleration is constant, which is actually, that was Galileo's famous experiment, right? He dropped like a golf ball and a bowling ball out of the Leaning Tower of Pisa, and they both fell. They both hit the ground at the same time. It's kind of hard to verify because of air resistance. So like theoretically, if you dropped a feather and a bowling ball, it should fall at the same rate. But the problem is there's air resistance, so that's why it looks like one falls faster. But really, they should fall at the same acceleration, at least as long as they're at the same elevation from the center of the Earth. So we're assuming that we're all at about the same elevation, so the acceleration of the gravity is constant. So it achieves a downward velocity of, well, it's the acceleration times however long it's been falling. So 9.8 t, all right? 9.8 times t, after time t, I should say. It achieves downward velocity of 9.8 t after time t. Okay. So find the distance traveled by the dropped kitten between 1 and 2 seconds. i.e., from t equals 1 to t equals 2. All right, we hold the kitten, let it go. It starts falling. Initially, we let it go at time 0, right? And I want to find how far did it fall between the first and the second second. Now, you might have noticed I used distance instead of displacement. In this case, they're the same thing because it's not like the kitten starts floating back upwards at any point. Yeah, I don't see that. Not like a flying squirrel or anything. Okay, so this will be the integral from 1 to 2 of v of t dt, according to our new displacement formulas. So this will be the integral from 1 to 2 of 9.8 t dt, which is 9.8. Yeah, hopefully you guys can all do this integral. If you can't, then as soon as lecture is done, you better make sure you can figure out how to do it. But that's t squared over 2, evaluated from 1 to 2. So what do we get here? We get 9.8 times 1/2 times 2 squared minus 1 squared. That's 9.8 times 1/2 times 3. And, whatever that is. 14.7. 14.7 meters is how far it fell between the first and the second second. And okay, so how about if the window that the kitten was dropped from is 100 meters high, I want to know how long is it going to take to hit the ground? 100 meters, that's what, like a football field more or less. How long do you think if you dropped a kitten? About how? Any guesses?
5 seconds.
About 5 seconds. That's a good guess. Yeah. Okay. If the window the kitten was dropped from is 100 meters high, how long till it hits the ground? So what we're going to do is we're going to set 100 equal to the integral from 0 and let's call it. Let's call the number that we want t. We want to find t. Big T, capital T, will be the integral from 0 to t of 9.8 p dt. Okay, so we already did this integral. This is 9.8 times 1/2 t squared from 0 to big T. This is 9.8 times 1/2 times capital T squared. And that's not very hard to solve. That gives us t squared equals 2 times 100 divided by 9.8. So t is the square root of all that. Let's see, this is approximately root 20, very roughly, right? This is about 2 times 10 is 20, so that's approximately, I don't know, 4.5. So 5 was a good guess, about 4.5, or at least my rough approximation is about 4.5 seconds. So yeah, now you'll know how long until you hear